Pluto is now proving to be a far more complex and dynamic world. Recent findings include evidence of hidden oceans, geological activity, and mysterious chemical patterns that defy explanation. These discoveries have left scientists both struck and deeply puzzled. At the heart of these revelations lies Sputnik Planitia, a vast heart-shaped region of nitrogen ice. Beneath its frozen surface may lie an immense liquid ocean, shielded by a thick layer of ice. This ocean, kept warm by internal heat, could be one of the most significant discoveries in the search for extraterrestrial life. Scientists speculate that microbial life could potentially exist in these hidden depths, thriving in conditions protected from the harshness of space. Pluto's surface itself is a dynamic and puzzling landscape. Towering ice mountains rivaling Earth's tallest peaks and vast smooth plains suggest recent geological activity. Heat from Pluto's radioactive core drives convection beneath its icy crust, causing nitrogen ice to move like a slow-freezing lava lamp. This unexpected level of activity challenges our understanding of what a distant icy world can be. Pluto also joins the growing list of icy worlds that might harbor life, alongside moons like Europa and Enceladus. Beneath its frozen crust, interactions between water and organic molecules could potentially spark life's chemistry. Even if advanced organisms are unlikely, the discovery of microbial life would reshape our understanding of habitability in the universe, proving that life can thrive in unexpected places. Pluto's relationship with its moon Charon is equally unique. Nearly equal in size, the two celestial bodies exert gravitational forces on each other, generating internal heat and dynamic changes. Charon's deep canyons and reddish hues suggest a shared history with Pluto, possibly involving material exchange between the two worlds, an interaction that may hold the building blocks of life. The James Webb Telescope's infrared capabilities have been crucial in these discoveries, revealing details invisible to previous missions. By analyzing Pluto's surface and atmosphere, Webb has detected organic compounds and temperature variations, painting a picture of a dynamic and surprising world. Pluto's atmosphere, though thin, undergoes dramatic changes during its elongated orbit, offering unique insights into distant worlds' atmospheric processes. Among Pluto's most intriguing features are its reddish spots, striking areas that stand out vividly against the otherwise icy and muted tones of the dwarf planet. These reddish hues are thought to be caused by a class of complex organic compounds known as tholins. Tholins form when ultraviolet light from the sun interacts with methane in Pluto's atmosphere or on its surface. This chemical process creates large, carbon-rich molecules that eventually settle onto the surface, giving it its distinctive coloration. These tholins are not unique to Pluto but are observed in other parts of the solar system, including the icy moon Titan and even in the upper atmosphere of gas giants. However, on Pluto, they present a fascinating puzzle tied to its unique environment and chemical interactions. What makes the presence of tholins so fascinating is their potential link to prebiotic chemistry, the chemical processes that precede the development of life. Prebiotic chemistry refers to the formation of organic molecules and reactions that could lead to the creation of amino acids, nucleotides, and other fundamental building blocks of life. The reddish tholins on Pluto might not only be coloring the landscape but could also represent the early stages of chemical evolution. This raises the tantalizing question of whether such processes, occurring in an environment as extreme as Pluto, could lead to the formation of life or its precursors. Scientists are particularly eager to explore how these tholins interact with other elements on Pluto, especially water ice. Beneath Pluto's icy crust lies the possibility of a vast hidden ocean, kept in a liquid state by the heat generated from radioactive decay in the dwarf planet's core. If tholins carried by geological processes or surface exchanges were to interact with liquid water, the chemical environment could become even more dynamic. Water acts as a solvent, facilitating chemical reactions that could lead to the formation of more complex organic molecules. These interactions could serve as a laboratory of sorts, where scientists can study how life might begin in conditions vastly different from Earth's. The potential implications of these interactions extend far beyond Pluto. If prebiotic chemistry involving tholins and water ice is happening on Pluto, it raises the likelihood that similar processes could occur on other icy bodies in the solar system, such as Europa, Enceladus, or Triton. This expands the scope of where scientists might search for the origins of life or its signs. Furthermore, it suggests that life, or at least the chemical precursors to life, might not be limited to planets or moons located within a star's habitable zone. Exploring these interactions will require future missions capable of probing Pluto's surface and subsurface. Robotic landers or even submarines designed to penetrate its icy crust and explore its hidden ocean could provide direct evidence of these processes. Analyzing samples of tholins and their potential interactions with water could yield groundbreaking insights into how life might arise under such extreme conditions. Pluto's reddish spots, once considered a minor curiosity, have become a focal point in understanding the chemical possibilities that lie at the intersection of organic molecules and the harshest environments in our solar system. One of the most revolutionary discoveries is the possibility of a vast subsurface ocean beneath miles of ice. This ocean, kept liquid by heat from radioactive decay in Pluto's core, could be similar to deep-sea hydrothermal vent environments on Earth, which teem with life. If Pluto's oceans host comparable conditions, they might harbor microbial life or even more complex ecosystems. The release of these findings has sparked excitement and speculation among scientists, governments, and the public. Pluto, once considered insignificant, is now at the forefront of exploration. Future missions, including orbital probes and landers, aim to delve deeper into its mysteries, potentially confirming the existence of its subsurface ocean and searching for signs of life. Pluto's geological activity is another enigma. Despite its distance from the Sun, radioactive decay within its core generates enough heat to maintain a liquid ocean and drive convection. Additionally, interactions with the solar wind create unique magnetic phenomena, providing rare insights into how small planets interact with their stellar surroundings. As humanity continues to explore the Kuiper Belt and beyond, Pluto has opened a door to new possibilities. Its dynamic geology, mysterious atmosphere, and potential for life challenge our understanding of distant worlds. The James Webb Telescope's findings remind us that even the most remote corners of the solar system hold secrets waiting to be uncovered. Pluto serves as a beacon of hope and possibility, a testament to the boundless curiosity and ingenuity of humanity. Once considered a distant, insignificant icy rock on the fringes of the solar system, Pluto has emerged as a focal point for scientific exploration and wonder. The tantalizing possibility that it could harbor life, or at least the chemical precursors to life, has reignited interest in the mysteries of this remote world. What secrets lie beneath its icy surface? Could its hidden ocean or unique geological features support microbial life? These questions drive not only scientific inquiry but also the development of new missions and cutting-edge technologies designed to probe the unknown. Every discovery about Pluto reshapes our understanding of the universe, challenging assumptions about where life might exist and how planets evolve in extreme conditions. From its dynamic geology to its mysterious reddish spots caused by organic compounds, Pluto has demonstrated that even the most unexpected places can be full of surprises. Its thin yet complex atmosphere and the potential presence of a subsurface ocean make it a prime candidate for future exploration. As new data continues to emerge, Pluto exemplifies how much remains to be learned about our cosmic neighbors, proving that the story of the solar system is far from complete. Pluto's mysteries remind us of the importance of daring to explore the unknown.